So now we look at two colligative properties that are calculated in a similar way. We're going to look at boiling point elevation and freezing point depression. One of the difficulties that we have when we're looking at how a quantity at temperature is modified in a solution versus in a pure solvent is that the volume of a solution will change with temperature. And you've probably heard of the idea of like a pipe undergoing what's called a freeze burst. And this happens because as we lower the temperature of a solution, of an aqueous solution, it can sometimes expand, and that can cause a pipe to burst, and it's the result of it can cause flooding at times. So when we're looking at the effect of a solid on a process where the temperature is changing, we need a measure of concentration that is independent of temperature, and there's a difficulty here. Molarity won't be able to do this because molarity is equal to moles divided by volume, and volume is affected by temperature. So molarity will also be affected by temperature. So we need a unit of concentration that is independent of temperature. So because molarity depends on the volume, it is not independent of temperature. So for that reason, we define a concentration term, or a system of concentration called the molality, which we give the symbol lowercase m, and molality is equal to the moles of solute per kilogram of solvent, and both of these terms in here are independent of T. So molality is a unit of concentration that is independent of T, unlike molarity. So we earlier defined that the normal boiling point, or the boiling point of a liquid, is defined as the temperature at which the vapor pressure equals the external pressure. And what we know is that if we add a solute, we lower vapor pressure. So that's going to affect the temperature at which boiling occurs, because you imagine that you've got a boiling liquid. What we know is that the vapor pressure equals the atmospheric pressure. Now if I add a solute, what's going to happen? The vapor pressure will get lowered and it won't be equal to the atmospheric pressure anymore, and the solution will stop boiling. So earlier we described that by adding a solute, we're going to lower the vapor pressure at a given temperature. So as a result, the presence of a solute results in an increase in the boiling point of the solution compared to the pure liquid. So if we had a liquid that was boiling, say this is boiling over here, again, as I said, the vapor pressure will equal the atmospheric pressure. Now, once we've added our solute, the vapor pressure will now be less than the atmospheric pressure. So it'll stop boiling, and in order to get it boiling, we're going to have to heat it up a little bit more. So this concept of boiling point elevation, it turns out that it is a colligative property. It depends only on the amount of solute added, and it's described by this equation, that the change in the boiling point is equal to the boiling point elevation constant multiplied by the molality of our solution. Now, it is important to recognize that we have to take into account the total number of solute particles, and that might be more than the number of formula units that we've added if we have something like an ionic compound that dissociates into multiple particles. So the Kb of water is 0.52 degrees Celsius per mole hour. And then we're asked, what is the boiling point of seawater if the concentration of ions is 1.15 molar? So delta TB, the change in the boiling point, is equal to the boiling point elevation constant of water multiplied by the molality. So this is going to be pretty simple to do. The change in boiling point will be 0.52 times 1.15. So the boiling point will be 0.598 degrees C higher than pure water. So pure water has a boiling point of 100 degrees Celsius, and then we get our little bit of elevation because of the ions that are present, and so the boiling point would be 100.598 degrees Celsius. So, seawater doesn't boil that hotter than regular water with no ions dissolved in it. So, experimentally it's observed that we also see an effect on the freezing point when we add the solid to a solution. And in particular, what we see is that the freezing point is depressed when we add a solid. So here we've got the lines. This is the liquid. This is the solid. So in here we have the regions where freezing is occurring. These are the pressures and temperatures where freezing is occurring, and you'll see that it's higher for pure water than what it is for an aqueous solution. So it gets shifted to lower values. So this is referred to as freezing point depression. So this is something that we take advantage of to stop our roads from freezing overnight in winter. So our roads get wet during the daytime and when it's relatively warm, and what we do is we add solute to that wet slush on our roads, and what that does is it forms an aqueous solution, and then hopefully overnight when the temperature drops, we've lowered the freezing point sufficiently of the water that it doesn't actually freeze. Now it's interesting to note that you'll see antifreeze and coolant often sold as exactly the same thing, and the reason is solutes, they increase boiling points, they cause boiling point elevation, i.e. they stop your car from overheating, it functions as a coolant, but they also decrease freezing point. That is, it's going to lower the freezing point and stop your radiator from freezing up. So it's the same stuff, right? It's actually a compound called ethylene glycol, which we've been talking about in some of our labs. So freezing point depression is a colligative property, and it's defined by an equation that's very similar to the boiling point elevation equation. The change in the freezing point is equal to the freezing point depression constant multiplied by the molality of our solution. We do have to recognize though that it's freezing point depression, right? So the freezing point is going to be going down, unlike the boiling point, which goes up. So I'm not going to give an example calculation because it's exactly the same as boiling point elevation. When a non-electrolyte is dissolved in water, we'll get 1 mole of solute for every 1 molar particle. So if I take something like methanol dissolved in water, for every mole of methanol that I add to my water, I'm going to get 1 mole of aqueous methanol. However, when I dissolve an electrolyte in water, for every formula unit that I add, I might get more than 1 solute particle. For example, if I add 1 mole of sodium chloride, I'll get 1 mole of sodium ions and 1 mole of chloride ions. That is, I'll get 2 moles of ions total. And I mentioned this previously, for every 1 formula unit of sodium chloride that I add, I get 2 moles of particles. So I have to be aware of that. So this is taken into account via this thing called the Van Hoff factor, which we indicate with the symbol I. And the Van Hoff factor is simply defined as the ratio of solute particles in solution to the number of formula units dissolved. So that's it, right? So I just equals how many moles of particles actually end up in solution for every mole of formula unit of the solute that you dissolved. And in that previous example for sodium chloride, that was going to be 2 to 1. Okay, so for every mole of sodium chloride dissolved, you get 2 moles of solute particles, right? One of those will give you one of those plus one of those equals 2 total. So the Van Hoff factor is just going to be 2 on 1 or 2. So those equations that we had previously for freezing point depression and boiling point elevation can now be modified to include the Van Hoff factor. So the Van Hoff factor, really what it is doing is it's giving you the extent to which free ions form when an electrolyte dissolves. Now for a non-electrolyte, something that doesn't make multiple particles when it's dissolved, for a non-electrolyte, I will just be equal to 1. So whenever they're talking about a non-electrolyte in these problems, then they're really just kind of letting you know that I equals 1. Now there is a slight complication. When the concentration in a solution of an ionic compound gets really, really high, those oppositely charged ions start pairing up because they attract one another. So what can happen is that we have less than complete dissociation of the ions. So if I have a relatively dilute solution of sodium chloride, the ions don't pair up at all, I would be 2. If I go to a much higher concentration of sodium ions and I start getting significant pairing up of the ions, then your I will be less than 2. And that can be an issue, particularly when you start getting really highly charged ions that attract one another a lot. So this diagram that follows will kind of indicate that. So what we've got here is these are, I believe they are 1 mole per liter and 0.1 mole per liter. These are only 0.1 mole per liter. Here it is, it's right here. 0.1 mole per kilogram, I should say, because they're molality solutions. And so what you would expect is if this compound dissociated, you'd get 3 sodiums and you'd get 1 phosphate. So you would get 4 ions for every 1 mole of sodium phosphate. So you would expect I would be 4, but in a 0.1 molar solution, I is actually 3 because not all of the ions dissociate. And that's happening to such a large extent there because you have a relatively highly charged ion here. Now if I go down to sodium chloride here, where we've got a +1 for the sodium and we've got a -1 for the chloride, you can see that we would predict that we're going to get 2 ions when 1 mole of this stuff is dissolved. We get a value that's pretty close to that, 1.9 for the actual Van Hoff factor. Now if I take the intermediate case here, where I got a +2 with a -1, you can see that I get a modest deviation from the ideal scenario, thinking that I would get 3 ions here, 2 chlorines, 2 chlorides and 1 calcium. I actually get some pairing up here. When I have a +2 with a -2, I get a lot of pairing up. Okay, the product of the so these ions, these highly charged ions, attract one another a lot. And then here we've got a +1 with a -2, so that's going to be similar to this guy, isn't it? So 3 and 2.3 there. So these guys are kind of similar because you've got similar charges involved. So what you see is these really highly charged ions, when we have that, we get like significant pairing up. Okay, so these problems are concerned with boiling point elevation and freezing point depression, and you should have a go at them before Wednesday's Zoom session.